Hi everyone. Let's take a step back and talk about classifying carbocations. So far we've talked about carbocation structure and how they're stabilized. I wanted you to think more about the electronic factors before we got into classification. So carbocations are classified by the number of direct carbon attachments that the carbocation itself is making and by its proximity to pi bonds, okay? So if you were to look at an alkyl carbocation, that means that the carbon that is positive is bonded to another sp3 carbon. Okay, that's where the alkyl component is coming from. And then we classify the carbocation according to how many direct carbon attachments it has. This has one other carbon attachment, therefore it is primary alkyl. However, this carbocation here has two direct carbon attachments, and therefore it would be secondary alkyl. Okay, and if there are no adjacent pi bonds, you just have sigma bonds, this would be stabilized only by hyperconjugation, which again was your sigma donation. Okay, and of course, if you have two adjacent carbons, you naturally have more bonds that can sigma donate than if you had a primary carbocation. And if you have a carbon that is positive that is bonded to three other carbons, that would be classified as tertiary, and accordingly, now there are more sigma bonds that could donate. We also have carbocations that we classify as allylic. Now this term allylic is coming from the fact that the carbon of positive charge is directly bonded to a pi system, okay? That positive charge is on the carbon adjacent to the pi system, and it's secondary because it's bonded to two carbons, secondary allylic. This would be an example of a primary allylic carbocation, primary allylic. And the thing about these guys is that they're stabilized via hyperconjugation and by resonance. We said in the last video, having that adjacent pi bond enabled resonance donation, this pi electron density that could also be donated into the empty p orbital. Now, what I want to stress here is that these allylic species have the positive charge on a carbon adjacent to a pi system, and that is not part of a benzene ring, okay? Because if you had a positive charge on a carbon adjacent to the pi system of the benzene ring, we call that a benzylic carbocation, okay? This is the benzylic position. This is not the benzylic position. This is the benzylic position. And benzylic carbocations are also resonance stabilized, okay? So we love allylic and benzylic positions. Now let's think about kind of their evil counterparts, the less stable counterparts, okay? This is what we would call a vinyl carbocation. If you have a positive charge directly on that pi bonded carbon as opposed to adjacent to it, we call that vinyl. And the vinyl carbocation is especially unstable. It is an sp hybridized carbon. In vinyl carbocations, there's a less effective hyperconjugation, and because this carbon has sp character, its hybridization status sp, it's effectively a higher electronegativity carbon, and therefore is also less stable, bearing a positive charge. Okay, kind of the evil, less stable counterpart here is what we could call an aryl, A-R-Y-L, or phenyl carbocation, okay, where the positive is directly on a benzene ring. Again, that would be sp hybridized. These are very unstable species, okay? Positive charge directly on a benzene ring, sp hybridization state. So we have allylic and benzylic. We love those. We have the resonance stabilization of the positive charge. Vinyl and aryl carbocations, no bueno. Those are unstable species. And then if the positive charge is on a carbon that's just adjacent to sp3 carbons and there's no pi bond directly to that atom, we call those alkyl, okay? Primary, secondary, and tertiary alkyl. And you'll hear me use that terminology throughout the video series here as we talk about carbocations. So it's very important that you be able to classify effectively, because we are going to get into how we rank carbocations, and it's very effective in your ranking and understanding of carbocations to toss in these terms aryl, vinyl, alkyl, allylic, and benzylic when creating your understanding of carbocation stability. Let's get into that next.